Okay, so the big challenge for the day is to guess ahead of time what is not going to work. Hopefully, my stylus works for the whole time, and my life would just be great. But this is still going to be a what's going to break this time production, right? Um, so first of all, a little logistics. There will be a quiz this coming Monday, um, April 6th. All right, and so on it is going to be. Oh, there we go. Um, Come on, stylus, work for me. So it'll be bearings, bearing life, bearing concepts, right? So it could be roller bearings, could be journal bearings. How long does it last? What does the load have to be? What will the life be? What will the load be? When will it break? What's the reliability? Stuff like that. All right. Now, unlike the previous one, we're going to hold a pretty strict schedule. I think everybody kind of learned their lesson, or at least 15 of you learned your lesson last week. So I'll have the usual office hours, 8:50 to 9:40. And then at 9:40, I'll go make a new cup of coffee and do it in the cycling world what they call a natural break. And then I'm going to have the review session, right, which I thought worked really well last time, 10:20, and that's going to be via WebEx, which works pretty well. And then we're going to write the quiz from 10 to 10:45, right? And this ends at 10:45. And then the quiz submission really ends at 10:45. Okay, and I want you guys to be good engineers. Don't plan on things going right. Um, so please end it now, and I will be objectively inflexible. Right, be disciplined. Right, give yourself 25 minutes here and 10 minutes here, and be sure you can get it right. Also, the discussion boards are up. So, unrelated to the quiz. Um, Alston and Josh have been great about answering questions on the discussion board. So, please use them. That way, it works better to do that than to email me. A, I'm just getting swamped with emails. B, um, well, they're just better than me anyway. So, it works out for everybody. Okay. So the shaft basics, right? So we've been talking about these all semester, but it's probably worth mentioning a few things here. Usually relatively long round pieces that rotate and transmit power, right? Somehow, but okay, there's always a but, right? It could remain stationary, right? We've done quite a bit of work with spindles and axle stubs, right, where the axle is just stationary and the wheel spins on top of it. It might not be round, right? It might be flexible, right? So the tool your dentist uses, well, a lot of times those are air tools, but oftentimes they're also driven by a flexible shaft, and the attachments for your Dremel, right? So you can get into weird corners and stuff like that. A few items that are commonly mounted on the shafts: gears. We've talked about that. Sprockets, and this would be not the Saturday Night Live skit, but for chains. Okay. And then, wow, this is just not going well. Let's see how that goes. Okay, pulleys. That would be for belts. I wonder if I just don't push down as hard, if that works better. Brakes, clutches. We'll talk about those later in the semester. So the rotating shafts are usually supported by bearings, right? Minimum of 2 bearings to carry the radial load, right? Because the bearings can't carry moments very well. At least they shouldn't. So we have 2 bearings so that there's no moments. All right, like that. And then normally one and only one bearing to carry the thrust load, right? We're not going to really do thrust bearings too much, so I'll just leave it at that. We've got a picture later on. Shaft design. All right, so here's two different kind of versions of a shaft. Now in this situation here, we've clamped the shaft. So this is like an axle stub, where there's some sort of hub, or in this case, it's a chain sprocket, right, that's mounted on 2 different bearings, right? And then so the hub is allowed to rotate relative to the shaft, right? And the shaft has some components here. Here's another example where here's the fixed part, right? This could be the axle. Or the trailer frame or the auto body or something like that. The whole shaft rotates, and then the chain spins on there, right? So this has important implications, right? Which one of these has a static load? Which one of these has alternating load? Which one has a mean load? So these are two very different approaches to doing the same thing. Things to consider. Of course, we have to consider static stress and fatigue. So this is the stuff that you've looked at heavily for your project. All right. And then, so some other things to consider are deflection, right? Why would I worry about deflection? Because if you've got bearings here, bearings don't handle being out of alignment very well. So it may be a situation, or maybe a very precision application where deflection would be bad. Also critical speed, right? So that would be vibrations slash resonance, right? So that's stuff to avoid. But again, our project is mostly revolves around this, and we're bending torsion, axial, and transverse shear. But for the project, we don't even worry about that too much. Okay, and so yeah, that's good for that. Okay, now, so there's two really important things we have to think about when we're designing shafts. The two things are, how do you hold the shaft components in place, right? So I have no idea what's going on here, right? I mean, what are these things? Probably some sort of pulleys with some sort of belts going on. How is this balancing here? That doesn't make any sense. So there must be something there, maybe some bearings. What keeps us from sliding back and forth, right? So the whole shaft can't slide back and forth. The pulleys can't slide back and forth on the shaft. Secondly, how do I transmit torque between the component and the shaft? Right? Is this welded on in place? Is this all machined out of one big chunk? Is this 3D printed? Or somehow is there something that attaches this pulley to the shaft so that the torque can be transmitted, right? Otherwise, the pulley would just spin relative to the shaft, and this one could just spin and whatever. All right. So, holding things in place axially, holding things in place rotationally, or transmitting torque. Right. More realistically, this is what it looks like. Right. So here is a shaft. It's very much, wow, this looks a lot like the counter shaft from your project, right? Where you've got some bearing here, you've got some bearing over here. What holds this bearing in place? Oh, there's a little shoulder there. It seems like we've done a lot of problems with shafts and shoulders, right? So there's a shoulder there that holds the bearing in place. And then there's some other weird stuff here. What is going on here exactly? I don't know. And then some other weird, actually similar sort of weird stuff here. Some weird stuff here going here. We got a shoulder here. Okay, that's nice. We've studied those. The shoulder holds this bearing in place. I don't know what that's all about. So that's, whoop. Come on, stop doing that. So this is what a real shaft would probably look like. All right, it's not going to look like, just that simple picture on the previous slide. Okay, so here's kind of a little summary. Common components include, right, gears. Yeah, that's what we're doing. Sprockets,